Hello everyone, and welcome to the video where we're going to talk about drawing organic molecule structures. So organic chemistry has a lot of carbons, and we're going to see that, and so we've come up with some shorthand to make it easier to follow, and I'm going to show you the 3 different ways that people most commonly represent organic molecules, and we're going to learn how to interchange between them. So first off, hopefully you've seen this document before. This is in the supplemental readings, so you can read through this, but we're also going to talk through it a little bit. So obviously you can read the top, but then the 3 different forms that we can have are Kekule or expanded form, condensed form, and line bond or skeletal form. So the one that we're going to use the most is this one on the bottom, skeletal, but to understand it, you really have to sort of go through the other ones first. So let's talk about those first. So the first one says for expanded form here on the top, all the bonds are shown, but lone pairs are not. Basically, this would be the same as if you were drawing a Lewis dot structure, it's just without the dots part and only the bonds. In this case, the molecule is neutral, but if there was a charge, a formal charge on any of the atoms, you'd want to make sure that you show that too. That's actually true for all 3 of these structures. You always want to show if there's a non-zero formal charge. And there are some examples of that on the practice problems. So next, let's look at condensed form. So for condensed form, you're showing all the atoms, but you do not show any of the bonds, unless it's a ring structure, that's an exception. But in this case, if you look at the structure on the right, all of this is supposed to be carbons connected to each other, and then there's hydrogens on there. So you want to show the hydrogens, but you're just not showing the bonds to it. And then you're supposed to know how things are connected. You have to know a little bit more about how things work to know exactly how they're connected. When you have something that is sticking up from the top or the bottom, you're going to use these parentheses. That means that it's attached to the side, but if it's just written in the line, then that's part of the main chain. So here we would have 1, 2, 3, 4 carbons in a main chain attached to an OH. So we'll sort of translate that here in a minute. But so that's sort of the idea. Now, it's important to note that condensed form was invented primarily for typewriters. Basically, people were writing articles about organic molecules and they wanted a way to be able to type what they did or have their secretaries type it because they probably didn't type it themselves. So they just wanted a way to make it type. Now that we have computers, there's really not a need in my mind for condensed formula, and as humans who can draw with their pens, we really don't use it a lot. So you'll see I don't use it a lot. Your textbook unfortunately does, and I couldn't find a 1 semester textbook that didn't use stupid condensed formula. So we're going to learn how to translate condensed form into line bond form, and then we're just going to work from that. Once you get the hang of line bond form, you're going to love it. It's so much easier to use, and all my students have always said that. By the end of the semester, they're like, why does anyone use anything but line bond form? It's the best. So hopefully you'll feel the same way. But we do have to know condensed because books use it and other people still use it, so we have to know what they're talking about. So now let's look at line bond form, also called skeletal form. So in this form, basically what you're doing is you're assuming that any point on a line is a carbon. So if you look here, we've got 1, 2, 3, 4 in the zigzag. Each of those points, I'll make a little dot here so you can tell, those are carbons. So because so many things are carbons, it just makes more sense to show them this way. It makes it easier to figure out what's going on. So those are the carbons. Then any place there's a carbon, the hydrogens are not shown because there's always so many hydrogens. If you look at this condensed, there's tons of hydrogens, but the hydrogens don't do anything. They don't really matter, to be honest. So they're just there. So we're just going to assume that we know that they're there. Because we know that carbon has to have 4 bonds in order to be neutral, notice there's no charge written on here. So if they're all neutral atoms, formal charge 0, that means that it has to have 4 bonds. So basically what you do is take each carbon and anything that's not aligned to a different atom is going to be a hydrogen. So here you would have 3 hydrogens. And on this carbon you have 1, 2, 3 bonds already, so you'd have 1 hydrogen. This one would have how many? 1 hydrogen, right? And then this one would have how many? 2, right? Because it's got 2 bonds, 1 to a carbon, 1 to a bromine, and then it's got 1 hydrogen. Note the bromine at the end is just a bromine. It's not a carbon and then a bromine, it's just a bromine. So you always show a line to other elements as well, but you just don't show the hydrogens. But everything else you'd want to show. Any atom that's not hydrogen is shown, and then any hydrogens attached to atoms that are not hydrogens are still also shown. So hydrogens can be on an OH, for example, but they just can't be on the carbon. So hopefully that makes sense, but let's do some examples to make sure. I'm always a big fan of doing examples. There's some other examples on the back of the supplemental, but let's break these three examples down a little bit further before we go on to talk about a few of those. So before I just turn you loose on a bunch of different practice problems, let's talk for a minute about how you would convert one form to another form. So let's do an example. At the bottom here, I'm going to do, let's call this example number 1, and we're going to convert the structure shown at the top right for the expanded form. Let's convert that to line bond, aka skeletal form. So the first thing that I would do is I would take from the structure on the left all of the carbons. If you look, they're in this shape that's a hexagon with an oxygen. But let's go ahead and make all of the carbons just points on the line. So basically I'm just going to draw a hexagon bottom like this. And then I'm going to add the oxygen in the top point of the hexagon, so that's still drawn. Remember we said that any element that's not carbon, you have to show it as the letter of whatever that element is, unless it's carbon or hydrogen. So we're going to put the oxygen, make sure you put that in there. All right, so then the next thing we want to do is check and see if we need to add anything else. So we've got our carbons, that's the points on the shape. And then the hydrogens, we actually don't need to add the hydrogens. So all the hydrogens that are on the carbons are basically just not shown. So then we're done. So that's all we have to do. So for the next example, I thought we'd do something with this condensed formula up here. So let's have that be example 2. We're going to turn this condensed formula here into the Kekule form of that same molecule. So we'll do that down here. So when you're doing condensed, I really find it easier if you number the chain, the long chain. So in this case, we've got 1, 2, 3, 4. I've already got the numbers there. Those are all the carbons that are attached to each other. Because there's no parentheses or anything, that's how we know they're in order, basically attached. And then this OH on the end is also attached to carbon 4. So just any of these numbers, I'm going to call them C2, that's carbon 2. So that way, just so you know what I'm talking about. So let's draw those carbons first for the Kekule expanded form. Remember, we're going to draw every atom and every line, just not the lone pairs. So I'm going to draw those carbons 1 through 4 first. Next, I'm going to add the OH. So I'm going to add a line for the O and then a line for the H, of course, because those are separate bonds. It doesn't matter which way those lines are really facing, so notice I had to put my H sort of pointing down a little bit just because of space. It'd be fine if you put it straight, it'd be fine if you put it like with a right angle up or down. That doesn't matter. All that matters is the connectivity of the lines, so as long as the lines are connected to the right thing, it's totally fine. Then I want to add anything that's off of that main chain, that's off to the side, and those are shown by the parentheses. So see over here where it says parentheses CH3, that's going to be on carbon 2. I've written that here. So carbon 2 is here, and then I'm going to add that off to the side. So add another carbon there. And then the last thing I'll do is add all the hydrogens. So carbon 1 obviously has 3 hydrogens on it, so let's add that there. That gives it 4 bonds, notice. For number 2, I should only have 1 more hydrogen, so that gives that 4 bonds. For number 3, it says I've got 2, so there's 2. And then for carbon 4, I've got 2, so there's 2. Don't forget to add the hydrogens to the CH3 that's sticking out the side, so we'll add those. So then all the hydrogens are added, and that would be the full expanded form. Let's do one more example just to round it out. We'll do this example with, we'll call it example 3, and we'll do the line bond. We'll start with that. Let's convert that to the condensed form of this molecule. Now, the easiest way to do this is actually first to convert it probably to the expanded form. I'll show you a shorthand how to skip that part, but for now let's do that, and then we'll use that to then convert to the condensed form. So here's what it's going to look like. So to do the expanded version, remember that each of these edges of the line are going to be a carbon. So then we'd have 1, 2, 3, 4 carbons. So let's go ahead and draw those since we're doing expanded first. And then we need to add the double bond. So there's a double bond there. And then we'll add the bromine that's on this carbon here. Okay. And then we just need to figure out how many hydrogens that we're going to add. So for this one, you can see this carbon only has 1 bond already, so it's going to need 3 more to give it an octet. So those are all going to be hydrogens, so we add 3 hydrogens. This one here has a double bond and a single bond, so that's taking up 6 electrons already. It only needs 1 more bond. So we're going to add 1 more hydrogen. So then by the same, obviously logic, we're going to have this carbon's going to have how many hydrogens? 1, right? And then how many hydrogens would be on this one? 2, right? Because it already has 2 bonds. Never add hydrogens to anything that's not a carbon when you're doing going from line bond to something else. They would already be there. So the only hydrogens you'll ever be adding will be to carbons. Just to make sure we're clear, I want to do what's called mapping to make sure we realize like what's the part on the top that matches the bottom. So what I'm going to do is I'm just going to number these carbons on the bottom structure that I've drawn. So this would be carbon 1, carbon 2, carbon 3, carbon 4. We don't number anything else but the main chain usually. You can number other ones if you want to. And there's no significance to where I started the one right now. That's not important. So we're just trying to match it. So if that's 1, 2, 3, 4, then on the structure above, this would be the 1. See how that matches? That's the carbon on the end, and then that's the carbon with the CH3. And then this would be carbon 2 where the double bond starts, carbon 3 where the double bond ends, and then carbon 4 which has the bromine attached. So that's how they match up. Sometimes that helps people to see it. We're going to do a lot of mapping in this class because it's a lot of visual learning, so hopefully that helps. So now that hopefully we can see how those match up, let's do the shortcut version of this. So instead of drawing out the expanded version every time, that's good practice for right now, but when you're on a test, by that time hopefully you practiced a little bit more, I'm going to show you the way to do it a little bit shorter. So if I take this structure, I'm going to redraw it down here. Now instead of redrawing everything, the carbons and everything, I'm just going to figure out how many hydrogens I need to add. So if I look here at carbon 1 on the end, I see that there's one bond, so I just go ///, that's 3 hydrogens. I'm just pretending they're hydrogens for right now. Not the real structure, just to give me an idea. Then carbon 2, I see it's got 1, 2, 3 bonds, so I add 1. This one has 1, 2, 3 bonds, so I add 1. This one has 1, 2 bonds, so I add 2. Much faster, just a shortcut. So not a final answer, but it really helps. So then the final step is I'm going to turn it into condensed form. So for right now, you can use what I drew up here with the expanded version, or you can use the shortcut version, but I'm going to use probably the expanded version for now, okay? So for this, I'm just going to type all of the carbons that are in the chain, and in this case, they're actually all in the chain. There's not even a side chain, so no parentheses this time, but I'll sort of show you how it's done. So basically, carbon 1 would just be CH3, so I just type that. You do the C first, and then the H is after whatever that carbon is. So then the next one would just be CH, the next one would just be CH, then the last one would be CH2. So that's all the carbons. Notice I didn't draw the double bond in between the CH and the CH. You could, but you don't have to, and that's the important thing. So if you ever see like a carbon that doesn't have enough bonds, that means that really it's supposed to have either double bond or triple bond. It's kind of hidden in this version, and that's just how it works. So I just want you to be aware that that's a possibility, so you want to keep an eye out for that. So then those are all my carbons. Then the last thing is I want to add my bromine. Now my bromine is attached to the main chain, and it doesn't need a parentheses. The reason it doesn't need a parentheses is because bromine is a single element, whereas when I added a CH3 on the previous example, that's more than one element that's attached to the side. So if it's just one element, don't use a parentheses like bromine or chlorine or fluorine. Those are the most common. But if there's more than one atom on the thing you're adding, that's when you need the parentheses like the CH3. So that's the difference there. So then that would be our final answer. That's the condensed form of this molecule. So that's the end of this video. Hopefully that cleared up how to do these things. There's some practice on the back of the supplemental, so you're welcome to try that, and then you can ask me any questions you have at the start of class. Then there's also another set of these that I have that I will post on the activities for Blackboard, and hopefully we'll have time to work on that in class a little bit. But either way, I hope you've had a good introduction to showing how we're going to draw and write our organic structures.